Thanks for the introduction. Good afternoon. I'm Ping. I'm with the Infrastructure Innovation Lab of Bydance. I've been there for almost 2 years. I've been working on software and hardware co-design projects, mostly for the infrastructure for AI machine learning these days. So it's really great to be here back again. I was here last year to talk about our evaluation with CXL memory and our learnings from the evaluation. Yeah, so this is the top of my the title of my talk. Before I start, a little disclaimer that I will be talking about the project. If you have any questions about the company, please reach out to our PR team. And also, the results are highly experimental, so they do not imply any product performance or roadmap. Okay, so the outline of my talk. I'll start with some background and motivation of the project, and then I'll present some results from our micro benchmark, so we can have an understanding about how their basic performance characteristics. Based on that, we also explore some use cases that benefit from CXL memory. And finally, I'll also discuss some of our learnings and our thoughts about how CXL can play an important role in the next generation memory architecture, especially in this AI and machine learning era. A little background about CXL. I believe most of you are already familiar with CXL, so I won't get into details here. Basically, it's a high-speed coherent interconnect between the CPU, memory, and all kinds of devices. So it's built on top of PCIe peripheral. And it's an open industry standard backed by many major players. So it's pretty promising ecosystem. Right now they have 3 major revisions: 1.1, 2.0, and 3.1. So there are 3 types of devices in CXL. Type 1, Type 2, and Type 3. So in our evaluation, we focused on Type 3, which is a memory expansion device. Okay, so why do we put together a team for this project? So first, we want to understand how this new hardware works in our real environment, the production server we use. We want to understand how they perform, especially the basic characteristics of the CXL on our real server, and also we want to evaluate this ASIC-based CXL product, which is close to mass production. And more importantly, we want to identify and explore some use cases that could benefit from CXL, which is very important for the adoption in the data center. So here is how we set up our experiments. So we're using our servers are based on Intel's Sapphire Rapids platform, which has CXL support. And we installed 1 terabyte of main memory on each server. And for CXL servers, we have additional 512 gigabytes of memory provided through the CXL memory expander card. So in our micro benchmark, we also leverage a feature called sub-NUMA clustering, or SNC. So the idea of SNC is that it will allow us to split a single NUMA node of our socket, in this case, into smaller sub-NUMA nodes, or they call it domains. So the CPU cores, the cache, and the memory channels are also split between these sub-nodes. So we set up SNC such that each domain has 2 local memory channels. So to match the two channels on CXL and expander, so that we can have a fair comparison between main memory and CXL memory. The tool we use is pretty standard. It's the memory latency checker from Intel. Here are some of the micro benchmark results. There are a lot of them, but these are a few of them. Yeah, let me just. Yeah, so we can see that we compare 4 different cases. The local DRAM and local CXL, meaning that we are accessing data from the same socket. And we also evaluate the remote access, which is accessing data from a different socket. So in general, CXL does perform slower than main memory. Is not surprisingly. It has longer latency and lower bandwidth cap. We also noticed that there is a nonlinear correlation between the bandwidth utilization and latency. So as we use up the bandwidth, as the bandwidth utilization goes higher, so above a certain threshold, we get exponentially growth in latency. So like in this chart, and also we noticed that the cross-socket access on CXL has a significantly lower bandwidth than local access. So in these two charts, so it's the drop is more than half. So we don't observe this such significant drop with main memory. So it's a very interesting observation here. Yeah, so a few more details. So some latency and bandwidth numbers. So basically the local access, CXL adds about 150 nanoseconds per day. But remote access is much slower, significantly slower. And also the bandwidth-wise, it's dropped by more than half. So, and again, we don't see this significant drop on main memory. So in summary, these are the 2 observations we see from our micro benchmark. So one is the nonlinear relationship between the latency and bandwidth utilization. And second, the significant performance drop when we access cross-socket. And per our discussion with Intel, it seems to be something to do with their hardware limitation in the CPU that we use. So this problem might be already resolved in the newer generation. Okay, so now with this, after this micro benchmark test, so we proceed to explore some use cases for that. We want to understand how they perform in the real applications and try to find some use cases that can benefit from CXL. Now, because the CXL memory offers extra capacity and extra bandwidth, right? So we categorize the use cases into 2. Capacity expansion and bandwidth expansion. So the first use case we explore is the in-memory database. So typically Redis, which is very common in our data center. Now in our evaluation we use an open source derivative of Redis called KeyDB. So and for these workloads, so it's very common that when they run out of memory capacity, they'll have to spill some of the data to SSD, which is a lot slower. Another option is that you can add more server nodes to a cluster, which is more expensive. So this is why we think the CXL memory can help you with the CXL's extra capacity on each server. We may be able to fit the working set in memory without having to add more servers. Yeah, so to understand the impact, so we compared several different cases. The baseline is, of course, everything is in main memory, and we also compared several cases with different ratios of data in spill to SSD and a different mixture of CXL and main memory using interleaving. And we also evaluated a kernel patch that dynamically migrate data between main memory and the CXL. Essentially, it's a memory tiering patch. we call it hot remote. So we can see that Spill to SSD is a lot slower, and also we noticed that the simple interleaving memory, main memory with CXL memory does not really perform well. In some cases, it's as slow as Spill to SSD. But with some proper tiering technique employed, we can achieve almost the same performance as all main memory configuration. Yeah, so the next use case we evaluate is the data analytical workloads or big data applications, which is also very common in our data center. We use the open source solution, Spark SQL here, and in these workloads, so there is a common stage called shuffling. When we join multiple tables, the memory footprint can grow beyond the memory capacity, and then you have to spill data to SSD, so similar to the in-memory database. So this could be one of the key dominant factor of performance. So similar, we want to see if CXL can help in these cases. Yeah, so we use the same similar methodology for in these experiments. So compare different cases of different ratios of spill to SSD and different mixture of main memory and CXL. So in big data analytical workloads, we see spill to SSD is a lot slower than main memory only. So sometimes more than 40 times slower. But with CXL plus main memory and memory tiering, so the performance gap is about 34%. So it's still slower than main memory, but it gives us some good trade-off between the performance and cost. Because in reality, the 100% main memory is infeasible for these workloads. It will be too expensive. So there will always be some data that you need to spill to SSD. So. And for these workloads, usually you have a performance target. You need to meet a certain QPS from the cluster. So in order to meet that QPS, you need a certain number of servers to meet that target. And we believe that with CXL's extra capacity, we can achieve a similar performance goal with less number of servers. And this can result in significant savings in our data analytical clusters. So we also came up with a cost model in our paper. If you're interested, you can take a look. I'll have the reference at the end of the slide. So another use case we evaluate is the infrastructure as a service. So it's a typical one, also like in the public cloud providers. So where the cloud providers will sell their VM instances to their customers. So in these applications, usually the VMs are configured or sold with a fixed CPU to memory ratio. We call it core to memory ratio. So for example, the EC2, for example, the EC2 instances here have a 1-to-4 ratio. So each vCPU is bundled with 4 gigabytes of memory. So, and we can imagine that with the fast-growing number of cores in recent CPU platforms, so it's getting harder and harder to keep this ratio. So because there is a limited number of DIMM slots on each server, and the total capacity of memory on each server is also capped. So when you run out of memory, some of the vCPUs cannot be sold. You lose the revenue. So this is also the case we think CXL memory can help. So it can help us to keep this core to memory ratio and increase the revenue of this IaaS computing. And we understand that the CXL memory is slower than main memory, but I think this performance gap may be mitigated with proper tiering and migration technique. And also, it could also be mitigated by proper pricing policies. Yeah, another interesting use case. This is actually a bandwidth expansion use case. We also evaluate CXL with a large language model inference application. So one major challenge to large language model inference is this high computation cost. So now, in order to make this generative AI applications sustainable, so it's very important. It's actually very critical to reduce the computation cost of inference. And KV cache, I'm not sure if you are familiar with this technique. KV cache is a very commonly used technique in large language model inference. So the idea of KV cache is pretty straightforward. So basically, due to the auto-regression nature of large language model, so there are a lot of redundant computation between your generation steps. So when you generate a token, your context is only one token different than the last generation step. Right? So most of your computation will be redundant. So if we can save the intermediate results, essentially the KV values, we are able to avoid these redundant computations and save a lot of inference cost. So I believe every generative AI application is using this technique these days. But the challenge is that this KV cache demands a high memory capacity and a high memory bandwidth. So you can imagine that when you serve many requests at the same time, each request will require their own KV cache because they have different contexts. So and you are reading and writing the many KV cache at the same time. So you're using a lot of memory bandwidth. So this will be a very challenging to memory's bandwidth. Now we evaluated this KV cache using an LLM inference application on our servers. We compare this with a baseline with only main memory, same capacity, but with one baseline using only main memory and our CXL server using main memory plus CXL. Okay, so the blue line here is the baseline. So you can see that we are only using the main memory here. So as we increase the parallelism, the number of threads, so the throughput capped at around 48 threads because we run out of memory bandwidth. So, but with CXL, so we can continue to scale the throughput. We continue to scale with more parallelism and achieve higher throughput than the baseline. So this clearly demonstrates the benefit of the extra bandwidth offered by CXL memory. So I think this is a very good use case. Could be a good use case for CXL memory in the near term. Okay, yeah, some of the insights we learned from our experiments. So we see very diversified application characteristics. So some of them are sensitive to latency, some of them need capacity, and some of them need bandwidth. So I believe for data center applications, majority of them are more sensitive to bandwidth. And also because due to the nonlinear correlation between the latency and bandwidth utilization, we are actually seeing the memory latency at load, not idle latency. So the idle latency on the memory spec could be misleading. So actual latency we see is the latency under certain bandwidth utilization. So this tells us that if we increase the total available bandwidth, we can reduce the bandwidth utilization and result in much lower latency as well. So this means that if the extra bandwidth offered by CXL memory not only helps those bandwidth sensitive applications, but also they also can benefit these latency sensitive applications as well. Yeah, and another insight we see is that we think CXL could be a key booster to new memory technologies. Why? Because the CXL decouples the memory devices from CPU. So the CPU can talk to any memory device. It doesn't matter what memory media is used. It could be DRAM or PRAM or SSD or anything else. So as long as the device talks CXL, so it can be plugged into the CXL fabric. So this means that the new memory technology does not have to rely on CPU support anymore. So they just need to be CXL compliant, and they can plug it into the ecosystem. So I think this will be a great opportunity for new memory technologies. I think this means a lot to me because I used to work on Optane. Yeah, so or it doesn't work. Okay, so yeah, so and also we also believe that CXL will be a key enabler of the next generation heterogeneous disaggregated memory architecture. So we see a trend that many devices are sharing a globally addressable and unified memory space, not only in the general computing domain, but also among the accelerators. So this is especially true in the HPC and AI machine learning applications. And also we noticed that with CXL we are seeing increased heterogeneity of memory, because now we have local memory, local main memory and local CXL memory and remote memory, and each memory can have different media. So the heterogeneity is increased with this new architecture. There are also a lot of challenges. Just to name a few, I think there's the scalability. For example, how do we scale beyond one rack? So right now, I think the CXL relies on the PCIe cable. That's very hard to scale beyond a rack. And also how to deal with hardware and software faults, because it's memory, so it can, if it fails, the program can crash. And we noticed that a lot of things need to be done on the software stack. I believe the community is already working on it. And also we need to think about the cost, because I think for the DRAM-based CXL memory, doesn't really have a cost advantage over local memory. It's still DRAM, and plus the extra cost of CXL hardware. So this will limit the application of CXL memory, because if it does not have a significant cost advantage. Now, that's why I think the new memory technology can help here. If we can have a new memory technology that is lower in cost and higher in capacity, and that is also CXL compliant, that would be a great fit for CXL. So again, huge opportunity for new memory technology. So in conclusion, we think CXL is a promising technology for the next generation memory architecture, and we did some micro benchmarks and to understand its basic characteristics, and we explored some new use cases with CXL memory, and also discuss the insights we learned from it, and our thoughts about how CXL can help transforming the memory architecture. And we also have a paper upcoming in a month. It will be published in Eurosys 24. So if you are interested, please take a look. And that concludes my talk. Thank you.